Now that we've been introduced to the concept of the heat capacity, let's now use the heat capacity to calculate the changes in internal energy and enthalpy in our systems. And so as we saw in the previous videos, we know by definition that the partial derivative of the internal energy with respect to temperature at a constant molar volume gives us the constant volume heat capacity. Right? That's just what the constant volume heat capacity is by definition. And so since we have this relationship here, what we could do is we could just do a little algebra and multiply both the left and the right hand side by dt. By doing that, this gives us the relationship that du is equal to cv dt. Alright? And then, if we switch from algebra to calculus, we could take the integral of both sides with respect to temperature. So if we integrate going from some T1 to some T2, we could do that on the left-hand side, and we could do that on the right-hand side. By taking this integral, this will give us our change in the internal energy, our delta U. Right? So that's all. That's what the relationship between delta U and CV is. It's related by an integral. Okay. In the same exact way, we could also calculate our delta H by doing this. So same thing for delta H. All right. But rather than the constant volume heat capacity, what we're going to use is the constant pressure heat capacity. So if we start with dH dt at constant P is equal to the constant pressure heat capacity, then our delta H is just going to be equal to that integral with respect to temperature from T1 to T2 of the constant pressure heat capacity with respect to temperature. Okay? So that's all we have to do in order to get delta H. But of course, the actual details of the math depend completely on whatever the mathematical forms of our CV and CP are. All right? And so CV and CP, depending on their state of matter, or even what type of chemical they are, their heat capacities are going to have different mathematical forms. So CV and CP are reported in different mathematical forms. Okay? Perhaps the easiest form to work with is the case where CV or CP are just constants. For example, let's say we were trying to calculate delta H. So that would just be equal to the integral of Cp dt from temperature 1 to temperature 2. But if Cp is a constant, then we could just take that outside the integral, and then all we would have to do is just integrate dt. And so that would just give us T2 minus T1. A very simple answer. All right. Now, you've seen this form of delta H before. All right. And so let's think back to the previous video where we defined and derived our CP. So think back to the constant pressure experiment. Right? And so if we think of delta H, just regular H, not the molar or the specific enthalpy, what that's going to be equal to is going to be the mass of our system times delta H hat. Right? just from definition. Okay? And so we know that delta H hat is just going to be the integral from t1 to t2 of some sort of Cp dt. But if this is a constant, then what we'll end up with is just m times Cp times t2 minus t1, or otherwise written as mCp delta t. Okay? And in our constant pressure experiment, we said that our delta H was just equal to that heat. Right? And so the equation we get is that the heat is just equal to mcat. Right? And so this is the same exact equation that you used in your general chemistry courses. Right? Q is equal to mcat. Of course, this is only valid when your Cp is equal to a constant. Okay? And for a lot of systems, Cp is not equal to a constant. For example, if we just take a look at the heat capacity of water versus temperature at constant pressure, so the constant pressure heat capacity, we see that we don't get a flat line. Rather, we see that the heat capacity forms like a parabolic equation. Right? And that's because for many systems, for many chemical species, the constant volume heat capacity and the constant pressure heat capacity are functions of temperature. Now, typically, CV or Cp can be described using some sort of empirical polynomial equation. Polynomial equations. Okay? And so your heat capacity will take on two common forms, where Cp is equal to lowercase a plus bt plus ct squared plus dt cubed, where all these letters here are constants. There's another form that's common as well, where Cp is equal to a plus b times t, but then c is going to be over t squared. Right? So once again, all these letters are constants. Okay? And so in order to calculate your heat capacity and vis-a-vis your delta H or delta U, you would need to look up what these constants are and then plug them in to your delta H equation and take the integral of them. Right? Fortunately for us, Table B2 in the back of the textbook lists a bunch of constants for a bunch of Cp constants for various chemical species, and for species in different phases as well, in some cases. Variety of molecules. And so if we jump to the back of the book, we could take a look at Table B2, and we see that it lists, for instance, for acetone, if you look at the kind of 4 columns on the right there, it lists the A value, the B value, the C value, and the D value. Right? And there, it also tells you which form of the equation to use, whether you use form 1 or form 2. Right? Okay? And so the one thing I want to point out with is when it lists the constants, you see that it says A times 10 to the 3, B times 10 to the 5th, C times 10 to the 8th, and D times 10 to the 12th. What that means is that the value that's listed in the table is actually, times, for instance, for A, it's times 10 to the 3 of the actual value. Right? So when you actually plug it into the equation, you're not going to type in 123. What you need to type in is 123 divided by 10 to the third, or 18.6 divided by 10 to the fifth. The reason they put it in the book this way is so that, they could put it in the table nice and cleanly. So I just wanted to point that out because that can be a source of confusion, and you don't want to type in your constants and be off by orders of magnitude.